Hello Calc 3, welcome back for another video. In this video we will be covering the first half of section 12.4. Section 12.4 is on the cross product, a new type of vector operation. So in the last section we defined a new kind of vector operation called the dot product. Remember that when we took the dot product of two vectors, it returned a scalar. In this video, we will define another vector operation called the cross product. And the cross product is going to return a vector. So let's get right to it. If we let u and v be vectors in space, and in particular we're going to be talking about three-dimensional vectors here, so vectors in space, then there is a plane that contains both the vector u and the vector v. So you can see that in the diagram below. Again, my drawing skills were not up to the task here, so I just took a picture from the book, this picture here, so you can see that the plane in gray contains both u and v. And when we take the cross product, which we will define soon, of the vectors u and v, which we write as u cross v, or u times v, we get another vector, and this vector, u cross v, is orthogonal to both u and v. So if you look at the diagram here, u and v are both lying in this gray plane, and the red vector in the picture is u cross v, and that vector is going to be perpendicular to both v and u. So to find the direction of the cross product of u and v, we're going to use the right hand rule. So open your hand and point your fingers along the vector u in the diagram here. And now I want you to take your fingers and curl them towards the vector v and stick your thumb straight up. Then the direction of u cross v is in the direction of your thumb. So in this case, u cross v is going up. If we would rearrange the vectors, so say you want to switch v and u. So in this diagram, let's cross out u here, let's make it v, and let's make this u. Now let's see what happens to the cross product using the right hand rule. So again, I want you to point your hand or your fingers in the direction of the vector u, and now curl your fingers towards the direction v. And you'll notice that this time your thumb is sticking down. So if we had the vectors oriented this way, the cross product would actually be pointing down as opposed to up. And this will lead into the interesting fact about the cross product, which is that the cross product is not commutative, unlike the dot product, which is commutative. And we'll talk about that in more depth when we get down to the properties of the cross product. Also note that we denote the unit vector in the direction of u cross v by this vector n. So if you go back up to the diagram, you can see it. That's the small arrow in the same direction as the vector u cross v. And now we can get to a definition of the cross product of two vectors. So if we let u and v be vectors in space, then the vector, which we will write u cross v, is given by the length of u times the length of v times sine of the angle between u and v, all multiplied by the unit vector in the direction of the right hand rule, which we just said was n. So notice that the magnitude of the cross product of u cross v is going to equal the length of u times the length of v times sine theta, and then the direction of u cross v is the same direction as this unit vector n. Okay, so here's an important note about the cross product. The cross product is only defined for vectors in three-dimensional space. To see why, think about having two vectors in the plane in two-dimensional space, call them u and v. What would it look like to have a third vector that is perpendicular to both u and v? Well, if we're in the plane, this is impossible because to make a vector that's perpendicular to both u and v, we have to leave the plane. We have to go into a higher dimension. And for this reason, the cross product is only defined for vectors in three-dimensional space, not for vectors in two-dimensional space. Okay, recall from the last video on the dot product, we found that two vectors were orthogonal if and only if the dot product of the two vectors was equal to 0. And analogous to this fact, now using the cross product, we have that two non-zero vectors are parallel if and only if their cross product is equal to 0. So I'll give a little proof of this, kind of like I did for the dot product. So let's let u and v be arbitrary non-zero vectors and assume that they are parallel. So first we'll do the forward direction, so we'll assume that the vectors are parallel, then show that their cross product is equal to 0, and after we're done with that, we'll do the backwards direction, assuming that u cross v is equal to 0 and showing that u is parallel with v. So again, assume that u and v are parallel, then theta is going to equal 0 or theta is equal to pi, because the fact that they're parallel means that they're lying on the same line. If theta is equal to 0, then u cross v is defined to be the length of u times the length of v times sine of theta, which in this case is the sine of 0. And of course, the sine of 0 is equal to 0, and we get that the cross product is equal to 0. If, on the other hand, theta is equal to pi, then u cross v is equal to the length of u times the length of v times the sine of pi. And again, the sine of pi is equal to 0. So if u and v are parallel vectors, then we have that the cross product of u and v is equal to 0. And now for the reverse direction, assume that u cross v is equal to 0. Then by definition, u cross v is equal to the length of u times the length of v times sine of theta, where theta is the angle between u and v. And we assumed that u and v are non-zero, which means that the length of u and the length of v are also non-zero. And this implies that sine of theta has to equal 0. And the only values of theta for which sine of theta is equal to 0 are theta equals 0 and theta equals pi. So if the cross product of u and v is equal to 0, then the angle between u and v is either 0 or pi. And in either case, u and v will be parallel with one another. So let's move on to some properties of the cross product, which I have listed here. Again, I don't want to go through all of these different properties. I just want to make them available for you, and they're also listed in the book, but I will mention some. So one important property, I guess I'll talk about one a little bit. So one just says that we can pull scalars out of the cross product from either u or v, or we can distribute scalars through the cross product. Or rather, I should say, we can move a scalar to either of the vectors that's being multiplied with the cross product. The property 2 just says that the cross product is distributive over vector addition, so that might be an interesting one to know. We also have property 4 here, which is distributivity in the other direction. So now we have our vector u on the right side of v plus w, and we still have distribution through there. And property 3 is probably the last one that I want to talk about here, one that I already mentioned previously, but notice that v cross u is not equal to u cross v generally. In fact, v cross u is equal to negative u cross v. That corresponds with the fact that when we switch the orientation of our vectors u and v in that diagram from before, we ended up with a cross product that pointed in the opposite direction. So again, the cross product is not commutative. And it's also good to note that the cross product is generally not associative either. So these are two different properties that we did have for the dot product, and the majority of operations actually that we perform on any kind of real numbers or scalars. So this is the first time where we have an operation that's a little bit funky. It's an operation that's not commutative and it's not generally associative. So here are just a few things, a few pieces of information that I want to give you. The book goes into this section here in a little bit more depth, but I don't want to get into it too much. I would just generally know the fact that the cross product of I and j is going to give you k, and the cross product of j and k is going to give you I, and the cross product of k and I is going to give you j. You can either just memorize these facts. If you want to, you could try and convince yourself that it's true just by plotting the standard unit vectors in a coordinate frame and then asking yourself, using the right hand rule, asking yourself what's going to happen when you take the cross product of each of them. That shouldn't be too tough of an exercise. If you want to, you can stop the video and just convince yourself that these three equations here are true. And also recall from before that the magnitude of the cross product, u cross v, is going to be equal to the length of u times the length of v times sine of the angle between u and v. And the goal here is to give a geometric interpretation for what's going on with the cross product. So consider the parallelogram that we're forming on the right here with the vectors u and v. So we just kind of complete the parallelogram so that this side over here is parallel with our vector u, and this side here is parallel with our vector v. So the area of this parallelogram is given by the length of the vector v. I probably should put arrows on these vectors. The length of the vector v times h, which is the height of the parallelogram, as I've given in red there. But using a little bit of trigonometry, we can see that h is equal to the magnitude of u times sine theta. And therefore, the area of the parallelogram is actually the length of u times the length of v times sine theta. And we already said that this was the magnitude of the cross product of u and v. So what this tells us is that the magnitude of the cross product of u and v is equal to the area of the parallelogram that's formed by u and v. So that's a little bit of a geometric interpretation of what's going on with the cross product, at least where we're getting the magnitude of the cross product. So for the last part of the video, for the first half of section 12.4, I want to talk about how we can find the cross product of two vectors u and v using the component form of u and v. So if we go back up to the definition of the cross product, notice that it's really easy to find the magnitude of the cross product because it's just the length of u times the length of v times sine of the angle between them. All of those things are relatively easy to find, especially if we're given vectors in component form. But this vector n, the normal vector, that can be a vector that's somewhat difficult to find if you're just given arbitrary vectors in component form. So we want to figure out a nicer way to calculate what the cross product is going to be when we're given vectors in this form here, in component form. So this whole big section that I have in purple here is just a derivation of what the cross product would be if you're given vectors in component form. The derivation here just uses properties that I had listed up in this box here. So it's really not too tough to do, but I will say that it's quite tedious, as you can tell from all of the scribbles I have across the screen. And just realistically, we probably shouldn't go through it in a video like this. So anyways, you can use properties from the box, properties of the cross product, to find that U cross V in component form is going to be this expression down here, which is relatively complicated, certainly more complicated than the dot product was. But there's actually a nicer way to remember this formula or to calculate the cross product of U and V given the components. That's not just remembering this formula. So we're going to find a different way to calculate U cross V. And to do that, we're going to use a little bit of linear algebra. So for those of you who have already taken linear algebra, or for those of you who are familiar with matrices and specifically determinants of matrices, this is probably going to make a lot of sense. For those of you who have not seen matrices before or have no experience with linear algebra, this is going to take some time to get used to. So I'm just letting you know right away, you're probably going to have to practice this multiple times with homework, and you might even have to read over this section multiple times to feel like you understand what's going on. So I'll start off by saying that if we have two vectors, u and v, and they're given in component form, then u cross v equals the determinant of this following matrix over here. So the first row of the matrix is consists of the vectors I, j, and k. And then the second row of the matrix consists of the components of u, and the third row of the matrix consists of the components of v. If you're really unfamiliar with what a matrix is, it's just an array of objects. So I'm literally just writing objects in rows, and that's going to be called a matrix. And these vertical lines that I've put on either side of the array of objects represents or denotes the fact that I'm taking the determinant of the matrix. If you don't know what a determinant is, that is okay. We'll talk about it enough to be able to use it in this context below. So again, we can represent U cross V as the determinant of a matrix, and ultimately this is going to make memorizing how to find U cross V in component form much easier than memorizing this equation given up here. Though theoretically you could just memorize the equation up there if you wanted to, that would be okay. Okay, so calculating the determinants of matrices. Well, let's split this into two cases. We're going to talk about determinants of 2 by 2 matrices and then determinants of 3 by 3 matrices. To find the determinant of a 3 by 3 matrix, we just break down the matrix into 2 by 2 matrices, and then it ends up just being a problem of finding the determinant of 2 by 2 matrices. So for 2 by 2 matrices, which I have written here as A, B, C, D, where the first row is A and B, and the second row is C and D, the determinant of that matrix is defined to be A times D minus B times C. So you can think about it as multiplying this diagonal and then subtracting the product of this diagonal. That's probably the best way to think about it. So this is something you want to memorize. This is the determinant of a 2 by 2 matrix. Now for a 3 by 3 matrix, the first thing we want to do when finding the determinant of a 3 by 3 matrix is go through all of the terms inside of the matrix, and you want to put a plus, minus, plus next to these terms in the first row, put a minus, plus, minus next to the terms in the second row, and then a plus, minus, plus next to the terms in the third row. You don't actually have to write this inside of your matrix. You just need to know that when you're doing the calculation here, we're going to bring out some of these terms. As you can see, I brought out the A1, the A2, and the A3. And when you bring out those terms, they're going to carry with them the sign that is assigned to them. So look here how I've assigned a plus to A1, and this term right here is positive. I've assigned a minus to A2, and this term here is negative. And then there's a plus for A3, and this term here is positive. This is not a coincidence. So when you take the determinant of a 3 by 3 matrix, you have to consider each of the terms inside of the matrix, whether it's a plus or minus. And to do that, you're going to kind of checkerboard the matrix with plus or minuses, starting with a plus at your top left term. Okay, so after we have decided which terms inside of the matrix are going to be positive and negative when we break down our 3 by 3 matrix into smaller matrices, now we're going to take the term A1, so that top left term, and we're going to multiply it. I should definitely use some different color here. So we're going to multiply it by the matrix, the 2 by 2 matrix that we get when we remove the rows and the column containing A1. So we're going to remove the first row because A1 is in the first row, and we're going to remove the first column because A1 is in the first column, and we end up with this 2 by 2 matrix B2, B3, C2, C3. Then we're going to have minus A2 because again we have a minus associated with A2. We assign a minus to A2. So we have minus A2, and now to find the 2 by 2 matrix being multiplied by A2, we are again going to remove column 1 because A2 is in column 1, and this time we're going, or excuse me, row 1. We're going to remove row 1 because A2 is in row 1, and we're going to remove column 2 because A2 is in column 2, and this time we end up with the matrix consisting of these terms. So B1, B3, and then C1, C3. And finally, we're going to have A3 multiplied by the 2 by 2 matrix B1, B2, C1, C2. And again, to get that 2 by 2 matrix, we locate A3 in our matrix, and then A3 is in row 1, so we get rid of the terms in row 1. A3 is in column 3, so we get rid of the terms in column 3, and the terms that are left are right here, B1, B2, C1, C2. And after we break down our 3 by 3 matrix into this form, now we can apply the formula for the determinant of 2 by 2 matrices to solve the determinants of all of these guys here. Okay, so I know that if you have never seen determinants before, that's probably difficult to understand right away. And I also know that I probably butchered a little bit of the explanation, especially what's going on with the pluses and minuses being assigned to different terms inside of the matrix. And for that reason, it's probably best to just go right into an example. If you can understand the example, that's good enough. You don't need to understand all of the technicality behind it. So let's say that we have a vector u and a vector v. They are given in component form, and we want to find u cross v. So to do that, we're going to find the determinant of this matrix right here. Okay, so remember this theorem up here. We have u cross v is equal to the determinant of the matrix, where the first row is our vectors I, j, and k. The second row is the components of u, and the third row is the components of v. So we just fill in the different variables here. So the first component of u is 2, the second component of u is 1, the third component of u is also 1. The first component of v is minus 4, the second component of v is 3, and the third component of v is 1. And now we want to find the determinant of that matrix. So we're going to take the term in the top left, our vector I, and we're going to multiply it by the determinant of the 2 by 2 matrix that we get when we cross out row 1 and column 1. And that ends up being this 2 by 2 matrix right here. That's why we have a 1, 1, 3, 1 listed here. Now, this minus sign pops up because we have implicitly assigned a minus sign to our J in the top row. Remember, we're going to make a lattice and kind of checkerboard plus and minuses around the matrix here. And for that reason, J is going to carry a minus sign with it when we move it over here. And to find the 2 by 2 matrix multiplied by J, again, we're going to remove the terms in row 1 and then remove the terms in column 2. And we are left with 2 minus 4 and 1, 1. So that explains where this matrix comes from. And lastly, we have K being multiplied by the 2 by 2 matrix 2, 1 for the first row and negative 4, 3 for the second row. And to find the 2 by 2 matrix that ought to be multiplied with K, again, we get rid of the terms in row 1 since K is in row 1. We get rid of the terms in column 3 since K is in column 3, and we're left with this 2 by 2 matrix. 2, 1, minus 4, 3. So notice that we are multiplying 2 by 2 matrices by each of the terms in the top row, where the first term is going to be positive, the second term we put a negative in front of it, and the third term is also going to be positive. Okay, and now we can apply the formula for finding the determinant of 2 by 2 matrices. So for this first matrix, 1, 1, 3, 1, we have 1 times 1 minus 3 times 1. So we multiply this diagonal and then subtract this diagonal. That'll give us a minus 2 ultimately. So the I component is going to be minus 2. Now for this matrix over here, we have a 2 times 1 minus a minus 4 times 1. So that'll give us a 2 plus 4. Yes, I think that will be 2 plus 4, and I think I just made a little bit of a mistake here. This should be a 6. And then lastly, let's find the determinant of the last matrix that shows up here. So we have 2 times 3 minus 4 times 1. That'll give us a 6 plus 4. And that'll make our kth component equal to 10. And note that V cross U, as opposed to U cross V, is going to be equal to negative U cross V. This is one of the properties of the cross product, which would be 2 times the standard vector I plus 8j minus 10k. So here we've just reversed the signs of the components that are given above. And I think this is the last example. Yes, this is the last example here. So the last example is going to be to find a unit vector u that's perpendicular to the plane containing these 3 points. We have the points 1, negative 1, 0, 2, 1, negative 1, and negative 1, 1, 2. So we're going to use the 3 points that are given to us to form 2 vectors in the plane. So we can just arbitrarily choose. I'm going to choose the vector from P to Q and the vector from P to R. Then a unit vector perpendicular to the plane would be given by the cross product of PQ and PR, because remember, the cross product of PQ and PR is going to be perpendicular to PQ and PR, so it'll be perpendicular to the plane containing them. And then we can divide the cross product of PQ and PR by the magnitude of PQ cross PR, and that'll give us a unit vector, which we're going to call U. Okay, so our vector PQ in component form is given by 2 minus 1, 1 minus negative 1, and minus 1 minus 0, where we're just taking the appropriate components of Q and subtracting the appropriate components of P, and that'll give us that PQ in component form is 1, 2, minus 1. And the vector PR, likewise, is minus 1, minus 1, 1 minus negative 1, 2 minus 0 in component form. And we use the same process there. So now we want to calculate the cross product of PQ and PR, now that we've put PQ and PR into component form. So to do that, we set up the matrix IJK, 1, 2, minus 1, negative 2, 2, 2. And we want to find the determinant of this matrix, and that'll give us the cross product of PQ and PR. So we have I times the 2 by 2 matrix 2 minus 1, 2, 2. You can see where that comes from here. Then we have minus J, remember the minus J times the 2 by 2 matrix 1 minus 1, negative 2, 2. Again, you can see where that comes from. And then we have K times the matrix 1, 2, negative 2, 2. And you can see where that comes from as well, just from removing the terms in the first row and the terms in the third row. And that is the 2 by 2 matrix we're left with. And now we want to calculate the determinants of each of these 2 by 2 matrices. So we have 2 times 2 minus 2 times negative 1 for the determinant of that matrix. That'll give us a 4 plus 2. For the determinant of the second matrix, we have 1 times 2 times negative 1 times negative 2. And that'll give us a 2 minus 2. And for K, for the 2 by 2 matrix associated with K here, we have 1 times 2 times 2 times negative 2. And that will give us a 2 plus 4 for our kth component. And now doing a little bit of adding, we end up finding that the cross product in component form is equal to 6i plus 6k. And finally, we can find the length of the cross products PQ and PR. To do that, we're going to take the components that we just found and square them, add them together, and then take the square root. And we end up finding that the magnitude of PQ cross PR is equal to 6 times the square root of 2. And for this reason, we said that U is equal to PQ cross PR divided by the magnitude of PQ cross PR. And that will give us 1 over 6 times the square root of 2 times our the cross product of PQ and PR in component form, which we just found. And now we can just factor through by that scalar 1 over 6 times the square root of 2. And we find that our unit vector perpendicular to the plane containing the 3 points is given by 1 over the square root of 2 times the vector I plus 1 over the square root of 2 times the vector k. All right, so that's the end of the material for the first half of section 12.4. I realized that this video contained a lot of material, and I think primarily the difficult aspect of this first half is going to be calculating the cross product using determinants. So if you are unfamiliar with that idea, I would do a bunch of different problems where you're calculating the cross product of two vectors. And if my explanation kind of ruined this for you, or if you didn't understand what I was saying when I went through how to find the determinant of a 3 by 3 matrix, then I would just encourage you to look it up online or open your book, and your book might give a more clear explanation of what's going on there. All right, so I will see you next time for the second half of section 12.4.